to the multiverse and parallel universe in popular culture lately. Do you think that something like this is a possibility?
So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. And it answers some neat questions, because what is the best bit of evidence for alien life? We don't have any evidence for alien life, is the answer. So in the past, so we've landed missions on Mars, for example, the Viking missions in the 1970s, there was some suggestion that there might be some chemical reactions that looked a bit like life, and then it turned out that it probably wasn't, because it's very difficult to distinguish geology and chemistry from biology when you don't know what the kind of biology is that you're looking for. And so the answer is we don't have any evidence of alien life, of life beyond Earth, but we're looking. So that's the answer. What's going to wipe out humans first? If I was to guess, I would say humans, and that's not supposed to be a joke. I think that the biggest threat to our civilization is us. So we have complete control over that, but it might not help us, which says something about our stupidity. Beyond that, threats from space. So if a comet came in from the outer solar system, as they do, and it happened to be aligned with Earth, it happened to hit Earth, then there's nothing we could do about it at the moment. Most of the asteroids, the big asteroids that cross the Earth's orbit, we've mapped, but there are a few maybe that we haven't. We're looking, so we're actively trying to do that. And if we see that one of those big asteroids might collide in the future, then we've got a bit of time, 10, 20 years, whatever it is, so we might be able to do something about it. We're going to have to leave the Earth at some point and spread out into the solar system and beyond. If we manage to do that, and we're at the point now where we're just about to start, I hope. So we're not far off being able to travel, build moon bases and then travel to Mars. We're quite a long way off going from Mars beyond the solar system maybe. We're a long way off doing travel possible. Great question. It's kind of obvious to say it's possible into the future, because of course that's what we're doing. We're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1G, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda galaxy, and then, which is 2 million light years away from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey. And you could do that calculation. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905, not even the theory of gravity. So time travel is possible into the future, and it's inevitable that you travel into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around. Complete agreement, but there is a theory with which most people agree, which is that it was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. And it's sort of a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn. But then that ring very quickly coalesced into the Moon. So we think that the Moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it about, I'm not sure the exact date, I think something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed.
I think maybe 200-300 million years after we were beginning to form.
Yeah, so.
Black holes are interesting because we have a place called the event horizon where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature, both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. So black holes are forcing us into a deeper understanding of what space and time are. And in that sense, I think it is fair to say that black holes are the keys to understanding the universe. And when you start to talk about the distance to the planets, or the distance to the sun, the so-called astronomical unit, 93 million miles. What does 93 million miles mean? So look at the moon. The moon is the same radius on the sky as the sun. You know that because of total solar eclipses. It is a coincidence based on the way that our solar system has evolved, but it's a nice coincidence. So we can perhaps conceive of what the sun looks like on the sky. 93 million miles away. You can fit 1 million Earths inside the sun. So how do we conceive of that? The radius is something like 100 times the radius of the Earth. That means that if you got in a passenger aircraft, well, it'd take something like a year to fly around the sun in a passenger aircraft. It becomes inconceivable. And the sun's quite a small star. So then we start to think of bigger distances. So the most distant object that we created, we built, the Voyager 1 spacecraft.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Is now well over 150 astronomical units from the Earth, 150 times the distance from the Earth to the Sun. What does that mean? It takes light over 22 hours to reach it. So a signal at the speed of light to go to the most distant object we are in communication with, which has been flying since the 1970s. And then we have 365 times that, a light year, which is to the frozen edge of the sun's influence, the edge of the Oort cloud. 4 times further than that, you get to the nearest star, the Proxima Centauri, the Alpha Centauri system. That star about 4 light years away or so. So that's inconceivable. And then you start to talk about a galaxy then, the Milky Way galaxy. We're all in orbit around the center of the Milky Way galaxy. How big is this collection of stars? Somewhere between 200 and 400 billion suns in the Milky Way galaxy. About 100,000 light years across. And then you say, well, what about the nearest galaxy? So you go outside on a clear night where there's no moon and it's dark, away from the city lights. And if you know where to look, you can just about see our nearest neighbouring large galaxy. It's called the Andromeda Galaxy. That galaxy is 2.5 million light years away. It means the light entering your eye began its journey before we had evolved on Earth.